Welcome. This is PHY 2049L laboratory, and we're going to do reflection, refraction. We're going to try and do deviation and dispersion as well. It's a dry lab, meant that you couldn't be here today. We're going to try something slightly different. We're going to try and actually gather the data using a simulation program that's online and sponsored by, it's called PHET. And I'm going to try and show you that as we go through. My cat's just arrived, so you might hear some stuff going on. So I'm going to just see how this works. It won't be perfect, but it might be all right. So I'm going to go here. I'm going to step back and try and show you what's going on. So I typed in PHET using Google, and this is the website, and it's done by University of Colorado at Boulder. And then I clicked on physics, and there's all these simulation programs, and I'm going to pick on this one, bending of light. And you can download this, or you can run it as you can embed it, but it's basically we're just going to run it live. I'm going to start off with the introduction. And the first time I started using these things, I didn't particularly like them because I didn't get much out of it. And the reason I didn't get much out of it was because I wasn't managing them right. So let's just go back here for a second. Come on, cat. Let's do an objective, just so we're clear. So so this is lab, I don't know, 11, 12, something like that. Depends on the semester. And this is reflection, refraction, deviation, and dispersion. And as always, you're going to put down the date and you're going to put down the page number. And then our objective today, we investigate reflection, refraction, deviation, and dispersion using the PHET website. Cool. And I'm going to go back to, so what we're going to have is a series of exercises. So I'm going to go to the next page, and we're going to have reflection. Now you can't print out what we're doing. You can actually go to the website and you can do the experiment, but we're going to do it together because it's easier to do it with you than it is to actually tell you what to do. Let me explain what's going on here. We have a light source. This light kicks out a beam of light, and it's got rotation effects. I can see it as a wave, which is interesting, but I can see it as a ray. And I have two mediums. I have above, I have the first medium, which in this case at the moment is set to air. And I have the medium below, which is set to water, very standard way. And the first thing I'd like us to do is we've got to accept that this is showing reality. Otherwise, this doesn't work. So it's a simulation, and it's a good simulation. And what I'd like to do is just set up a situation. The way that Newton did this was he had a mirror rather than a denser material, optically denser material. He had a mirror, and he used pins. He didn't have a beam of light, he used pins. And he put 2 pins. Let's see if I wonder if I can write on this. Maybe I can, maybe I can't. No, I can't write on this. But he put, if you look where my arrow is, he put a pin here and a pin there. And then he looked into the mirror from the top right into the mirror, and he put 2 more pins in place. And we can do that in the lab, and it works out quite nicely. It's the traditional way of doing things, but then people developed light sources which give a beam of light, and so this became much easier. What I'd like to do is investigate reflection. And so what I'm going to do is I'm going to take a protractor and whoops a daisy. I'm going to I will get it lined up eventually. And then I'm going to take, say, an angle, like let's set this to 40 degrees. What I see is that, well, the angle of incidence is from the vertical normal, from the surface normal, around to where the beam of light is. So it's on this left-hand quadrant, if you like. And that's 40 degrees. And when I look, I see the right-hand quadrant is also 40 degrees. And if I go here to 60 degrees, I'm getting 60 degrees. If I go to 80 degrees, I'm getting 80 degrees. Okay, so there's my first lesson. Let's do a diagram of this. So we're going to have, I'm going to show it like that. That's the traditional way of showing a reflective surface. And I have my surface normal. And then I'm going to go here. You should be doing a ruler for this. In lab class, you would actually be tracing this off your experiment. But we measured that this was 40 degrees, and we found that was 40 degrees. This is incident, and this is reflected. And this is the normal, meaning at 90 degrees too, not the usual, but the normal. And this is the angle of reflection. And this here is the angle of incidence. And what we learned is for reflection, the angle of incidence equals the angle of reflection and the incident ray, the reflected ray, and the normal are all in the same plane. P-L-A-N-E? Yeah, I think so. Plane. So it's important to realize this is the angle of incidence. It's not the one to the surface, it's to the surface normal. And this is the angle of reflection. Now you're saying, doesn't matter. I mean, 40 equals 40, 50 equals 50. If I get the definition wrong, it doesn't matter. For this, it doesn't matter. But later on, it does for other things. So get it right the first time. So going back to our program, you know, we've seen this. Now let's play with this a little bit. What's going on here? Well, I'm getting reflection from an optically denser material. If I actually change the material refractive index, what you notice is that, well, don't know if you can see it very well. Don't worry about the stuff that's going on in the water. It seems to me that the reflected ray is getting stronger. Let's test that out. As I make these materials more similar, I get less reflection. And as I make the materials different, air versus water, air versus glass, I get more reflection. I don't get 100%, it's not like a mirror, but there's enough that I can sometimes need to take it into account. So that's interesting. And then the other thing I wanted to show you was waves. And what's happening is these waves coming along, and we're getting just the wave is reflecting off the surface. Let's, I don't know where you go, actually. There, okay. So the wave is just reflecting on the surface. What I'd like to begin looking at now is the ray inside the lower medium, which is refracted. So I'm going to go back to ray. I'm going to go over here. I'm going to say this one. So I'm going to say refraction. And for refraction, we have one medium which has a refractive index of N1 and another medium which has a refractive index of N2. So there's a few things we have to learn here. N, refractive index, whoops, is equal to the velocity of the light in vacuum over the velocity of light in the medium. It's a measure of how much the light slows down. If the refractive index is 1, then inside the medium the light travels at the speed of light in vacuum, 3 times 10 to the 8 meters per second. If the refractive index is 2, then what happens is the velocity within the medium is half the speed of light in vacuum. So it's traveling at 1.5 times 10 to the 8 meters per second. So it seems backwards for most people. Most people say, why wasn't it the other way around? And I've not got a good answer for that. But refractive indices, as far as we're concerned, are going to be bigger than 1 or bigger, because transparent materials slow down the speed of light. Okay, so we have an N1 for the top and M1 for the bottom, and it's useful to kind of have these pictures in your mind. So I tend to think of the top as being like a fish tank, so it would be air, which is so close to the vacuum value that we just call it 1. It's 1.0000, and then there's some other numbers in there, but it's speed of light in air is pretty much the same as speed of light in vacuum. And then let's say let's say this is air, then let's say this is water. And so we need a line between those two. And then we have a surface normal comes in. And then I go to my beam, and I send my beam in. And let's say that this is at 40 degrees. So my angle of incidence is 40 degrees. Yes, there's an angle of reflection at 40 degrees, but I'm not interested in that today. I'm interested in what happens to this ray when it continues. And it doesn't go in a straight line because these two refractive indices are not going to be the same. It's going to bend more towards the surface or more away from the surface. And the way it works is if you're going from a low end medium to a higher end medium, you bend away from the surface. And this here is my angle of refraction, not reflection, but my angle of refraction. I'd like to find the relationship between the angle of incidence the angle of refraction, N1 and N2. Let's go to the, usually the angle is, might as well put it in, 1.33. Usually the N value for water is 1.33. Let's go back to the experiment. And okay, I'm going to put my protractor back. And I'm going to make this 40 degrees. And I have air, which has a refractive index of 1 if you look at where my pointer is pointing. And then I have custom, and it's on water. So I want 1.33, and it's there on that one. So my angle of incidence is 40, and my angle of refraction is going to be 10, 20, I'd say 28 degrees. So let's go back here and say incident is equal to 40 degrees. Refraction is equal to 28 degrees. Now, there's a law which links these things together. It's called Snell's law. And it says N1 sine theta 1 is equal to N2 sine theta 2. So let's see if that works out. Let's pretend we don't know what N2 is. So let's pretend we don't know that. We'd say 1 times sine 40 is equal to N2 times sine 28. So N2 is equal to 1 sine 40 over sine 28. So N2 is equal to, let's go 1 times sine, I'm on degrees, 40, enter, divided by sine 28, enter. And I'm getting 1.37. Not 1.33. Let's just play a game with this. Sine 40 divided by sine, and rather than saying 28, let's say it was 27. Let's see what we'd get. I don't know if I did that right. Sine 40, enter, divided by sine 27. And I'm at 1.4. And if I went to, rather than 28 degrees, if I went to 29, sine 40 divided by sine 29, enter 0.99. So a little bit of a change makes a big change in the value of n2. So that's a reasonable answer then. It's not far out. It's in reasonable agreement. The values of n2 are in reasonable agreement. Just 1 degree either way would make a big difference, bigger than the difference that we're looking at there. So that's a good answer. Let's go back and have a quick look. Cat. My cat's kind of like messing with me now. Okay, let's change things a bit. So let's bring this down to 20 degrees. Sorry, 70 degrees. And let's change the material underneath. Let's change it to glass, say 1.5. And again, try and do that similar kind of thing. So I'm at 70 degrees and I have 1.5. So I'm going to go here. I'm going to go refraction 2. I'm going 70 degrees and n1 equals 1 and n2 equals 1.5, and I want to know that angle. n1 sine theta 1 equals n2 sine theta 2. Let's now pretend we don't know the angle. So I can say 1 sine 70 is equal to 1.5 sine theta 2. So sine theta 2 is equal to 1 sine 70 over 1.5, and this equals 1 sine 70, enter, divided by 1.5, enter. So that's equal to 0.63 actually. So theta 2 is equal to sine to the minus 1 of 0.63, which equals second sine, second answer equals 38.8. So that's what I'm predicting is this angle of refraction. Let's go back to our experiment. And yeah, 10, 20, 30. That looks like 38 point something. I can't get it quite as close as that. So this seems to work. Snell's law seems to work for this simulation. Not surprising. I'm sure the simulation is based on Snell's law. But it's the way the reality works. I want to mess with it just before I leave it. Notice what happens as I change the second medium. If I go to a bigger difference, if it's air going into air, there's no refraction whatsoever, and as the refractive index of the lower medium becomes bigger, so I get more of a change in the direction. I get a smaller refracted angle, but I get a bigger change in direction. Small effect, big effect. If I did not have air at the top, if I had water, for example, now, well, if I have the same medium at the top, no effect, but if I have water at the top, I can see that there's a smaller effect. I can see the way the effect goes. I'm still refracting more towards the normal. Can you see my refractive index at the top, 1.33, is bigger than my is smaller than my refractive index underneath, and so I'm bending towards the normal. I think that's a useful thing to remember. So what I do is I just imagine a situation like this, and I remember air and something like water, and I remember, oh yeah, that ray bends towards the surface normal. But now let's switch things. Let's put water over air. Oh, can't do it too much. And you see that I get this thing bending away from the normal, going more towards the surface. So that's interesting. That's very interesting. Snell's law again applies. Cool. Okay. So I think we've done what we need to do so far. Let's go to this next device. I'm going to put in here a block of glass, and I'm going to roll this around. I'm going to move it. I'm going to turn the beam on. Let me see if I want to get the biggest effect I can get. Look at that. I am getting refraction at this left-hand edge, and because I'm going from a low refractive index medium air to a higher refractive index medium, it doesn't actually say, does it? Oh, glass, it's down here, glass. Then I'm getting it bending towards the surface normal inside the glass. But then I'm reversing the situation. I'm going from glass to air. So what I do at the left-hand surface, I undo at the right-hand surface. And I can prove this, hopefully. Surely we have a protractor somewhere. Please give me a protractor. Please give me a protractor. Protractor, and hidden away. So now, a bit of an issue here. It's what happens with protractors. Oh well, we can do it. Protractors are the most misunderstood device because they've got numbers on them, but the best thing to do is to count. If I had left that like that and I just read the scale, then my values will be incorrect, because I need to measure from the surface normal, and it's saying 90 degrees by the surface normal. Now, I can twist it, but people sometimes forget to do that. So let's have a look. I'm going to make this on something that I can, I didn't mean to do that, but I did mean to do that. I'm going to have to live with it, aren't I? Yeah, okay. So, the cat's attacking me again. So, let's have a look. Let's get that a bit more rounded. Okay. So if I look at this, it's a little bit hard to, it seems very hard to get sorted out, but I can do it. So if I look at this, I'm on from the surface normal, 10, 20, 30, 40, I'd say 48 degrees. So it's the angle of incidence is 48 degrees. I didn't mean to do that as well. So the angle of incidence is 48 degrees. And then let's take you. Why can I not move you? Oh, there you go. And then, oh man, life. and then here 30, 40, 48 degrees. Can you see where my pointer is pointing? 48 degrees. So with parallel blocks, what happens at one face is undone at the other. So let's put down here parallel glass block. My cat is pulling on my sleeve with all its might, and it's my right sleeve it's pulling on, which is a problem. It's almost dinner time, so the cat is like determined to get fed, as if I don't normally feed her. Make those rays look parallel. And what we got was 48 degrees, 48 degrees. You know, use a ruler for it, but you know, the exit ray is offset but parallel to the incident ray. The ray that's approaching and the ray that are leaving, the exit ray, is parallel and offset to the incident ray. And I can kind of show that if I act together. They're parallel to each other. Offset but parallel. That's kind of interesting. Supposing these things are not parallel. Let's go back to the simulation. Let's get rid of the protractor. Oh, one final thing. Let's get rid of that. If I change this, they still stay parallel. They're just not the same offset. Okay. Let's take you and put it back in the toolbox, and then let's get this guy out. And then let's get that guy and move it. And do something like that. Okay. Okay. So now I have a glass prism. And what happens at one interface is not cancelled out at the other interface. And so we end up with a complete change in direction. And I'm going to make this not quite so intense. And so I can define the difference between the angle, between the direction of the original ray and the direction of the emerging ray or the exit ray. And I call that angle the angle of deviation. So let me go to the next page. So this is going to be, oops-a-daisy, angle of deviation. And it's like this. Again, use a ruler. The other cat's coming. And if I draw that on there, then it's the angle of deviation. Now, first of all, the angle of deviation is if you think about it, if you project that guy there, the angle of deviation is this little guy in here. It's somewhere inside the glass. And there's not one angle of deviation for one prism. If I come through here, if you look by changing the front ray slightly, I change the back ray a lot. It's like that's almost, well, that's probably what, that's probably, let's get the protractor and put it on. So I'm going to put the protractor kind of, it's a bit hard, but I've got to point to where I think it's going to be and then turn it around. So that angle of deviation is something like 90, 120, about 125 degrees. Between the incoming and the outgoing is about 125 degrees. And if I change this, this is again a bit harder to do, but if I change that so I get that more like that, let's have a look. That's slightly different. It's actually not as different as I thought it was going to be. Keep moving the wrong thing, of course. It's not as different as I thought it was going to be, but it's slightly different. So you don't get the same angle of deviation for a given prism. So what can we do with this? Well, one of the questions that I have and you can work this out by working out using Snell's law for the first interface and Snell's law for the second interface and then doing geometry. But one of the things you can do is I'm going to draw this again. I can give you this angle at the top. Let's say that's going to be 40 degrees. And then I can give you the angle here. And let's say this is, well, I can give you whichever one I like. But let's say I say that this angle here is 30 degrees. And then I say this is 40 degrees. And then I say, what's the angle of deviation? So the first thing you've got to do is be able to visualize where the angle of deviation is. And it's there. And then you've got to be able to find it. Well, it's all about the triangle in the middle. It's all about that triangle. And I know from geometry that this angle here must be 40 because I have a straight line and I have a straight line. Yes, I have a straight line and a straight line. So I've got to find this angle at the top. And the way I find the angle at the top is I say, if the angle down here is 30, the angle there is 30. And 30 and 40 make 70. So this angle here is 110 degrees. And if that is 110 degrees, then this angle on the other side must be 70 degrees. So I went 30 degrees here, plus 40 degrees that I was given, makes 70. Triangle has 180 degrees in, so this must be 110. Straight line has 180 degrees in, so that must be 70. So I have that 70, and I have that 40 in a triangle. So I say the angle of deviation is equal to 180 minus 70 plus 40, which equals 180 minus 110. So my angle of deviation is equal to 70 degrees. And that could be a test question. That's a pretty straightforward test question. Cool. Going back to our machine, our computer program, The next thing I'd like to look at is this. Let's get rid of view, and then let's go back here. I want you to see what happens when I change the color. Now, the refractive index is not only material dependent, but it's very slightly color dependent. Color is frequency. And watch what happens to this exiting ray as I change the color of the light. Let me do that quickly. Can you see that difference? It's going from red all the way to violet. Red all the way to violet. It changes because the refractive index of the air, well, it's still 1, but the glass is still 1. And if I were to make this thing, well, it's probably, I wonder if I can put a number in. Not sure I can. Okay, probably as big as it can get. Okay, so I'm getting the biggest effect I can get. It moves slightly. And let's do an experiment. Let's set this up first. I'm almost there. So this is angle of dispersion. And I have a red, so let's bring in a black beam just for the sake of it. Black beam goes like this. Now I can never remember which way around it goes. I should, but I cannot, so let me just remember. So the red was less bent than the blue. So I'm going to do my red beam. The cat's now going to the bathroom, so just so you know. And then we have the blue. The things I do for science there. And then red. And this angle in between is the angle of dispersion. And if we look back at our computer program, can I measure that? Not so easily, because I have to draw it, and the reason I have to draw it is this. If you think about it, to get the angle of dispersion, I got to backtrace these guys. So I've got to put my protractor somewhere like that, but I don't know where that point is. So I can't actually do a measurement on this using the computer program. If I could draw it out and trace it, then I could do it, but I just can't do that today. But you could imagine getting this program, and you could imagine taking that image and then taking that image and superimposing them and back projecting those two rays and getting the angle of dispersion. Now, why do we care about this angle of dispersion? We care about it because it happens whenever you get things that are triangular shaped or things that are not parallel. And so it happens with lenses. And I think I can maybe, let's have a look. Let me have a quick look at this. I think I can maybe show this to some extent. If I bring you around like that, let's get you nice and straight. Okay. Okay. And then let's go like that. And notice where this focal point is. And then let's see if I can see that move. Ever so slightly. If you look, you can see that just move ever so slightly. I swear I can see it move ever so slightly. And the problem is when you get different, maybe I can show it more like that. Yeah, you can see that wiggling a little bit. And so what happens is the red hues of your image will focus at different places to the blue hues of your image when you're looking through optical devices like lenses. And so you get chromatic aberration, which is a real issue. In fact, when they first started making telescopes back in, well, it's Galileo's time, so 1608, they made bigger and bigger telescopes, more light gathering power, but the problem they had was they couldn't do really curvy lenses, because if they did really curvy lenses, they would see this rainbow effect inside the telescope. So they made the lenses relatively non-curvy, but used big distances to try and get the effect. Now we can make a telescope that's made out of glass quite short because we can specially coat the lenses to compensate for this effect. And that was the genius of Newton. Newton came along with the reflecting telescope in about, well, he was about, what would he be? He'd be 1675, something like that. He was like the grandchildren's generation from Galileo. And it didn't suffer from any of these chromatic aberrations. Huge change. A little telescope, which looked like a toy, could do exactly what a huge telescope could do made of glass. And at first, the people who were good at telescopes looked at Newton's telescope and said, it's a toy. I remember, just by the by, I bought a Macintosh computer when they first came out, and I took it to work, and all the DEC people who were like mainframe with terminals just looked at it and laughed and said, yeah, what a waste of money it was. And then even there were some IBM people around, and they were like, oh man, it's such a little keypad and mouse and all that. And then, within 5 years, the Windows system had become like the OS system. And all right, now it wasn't a little toy, now it was a computer that was powerful. Sometimes when you see something that you're not familiar with, there's a tendency to undervalue it. And people did that with Newton's telescope. Hooke did it, and he never quite recovered from the effect that had in his life, because Newton got even with him. So those are the things that I want to do for today. We'll call this the first lab. What do? You need to make sure you're comfortable with, let's go back, I'm showing the wrong slide. You need to make sure you're comfortable with the physics we've been talking about. Know the angle of dispersion, know how you can find the angle of deviation and know what it is. Know that parallel glass blocks or plastic blocks or whatever will give you an offset beam but in the same direction. Know how to do good old Snell's law, and know the definition for the angle of, didn't show you any of that. Let's do that again. Know the angle of dispersion, know the angle of deviation, and know how to calculate it with a diagram. Know that for a parallel glass block, the two rays are offset from each other, but they are parallel to each other. Know how to work out good old Snell's law. That's for sure going to come up. And then know the angle of reflection. Know the definition of the angle of reflection. People forget the second bit. The reflected ray and the normal, the incident ray, the reflected ray and the normal are all in the same plane. There are other things I could show you. There's one more thing I want to show you. So let's just add one more thing. I've got a few minutes, so let's do that. I want to actually use this with one ray. I want to turn it around. I want to bring this down here. I want to turn that around. I want you to watch what happens. Did you see that? So imagine that I've got a semicircle of focus there. Yeah, not quite. I'll get there. I think this circle is... I'm trying to find where the middle of this circle is. No. I'm going to have to keep realigning. Notice, look at this. I'm getting refraction. Let's look at that point from here. I'm getting refraction. I'm getting refraction. Can you see how it happens so quickly? There's a point where I'm looking at this middle bit here. I'm not getting any refraction at the edge because I'm making it the angle of incidence is 0 and the angle of refraction is 0. But look at this. I'm getting, again, I'm going from a dense medium to a less dense medium, and I'm curving away from the normal. But look how far I'm curving away from the normal. And there. I will get there just a little bit. It will there. You go from refraction to reflection, and it happens at the critical angle. So let's just add a slide about that. So let me see if I can do this. Please let me insert new slide. So let's do a quick note. We've got 8 minutes. So let's do a quick note. Critical angle and total internal reflection. Let's just show, I don't need to draw the semicircle. Let's draw 3 examples. Let's do 4 examples. 1, 2, 3, 4. And this is, say, water, and that's air. That's the way I remember it. And I'm going to have a ray, and it comes up like this. And because it's leaving the denser medium, rather than going in a straight line, it bends slightly away from it. That will be the straight through direction, and it bends that way. And if I make this angle a bit more serious, it bends a bit more. And then there's a critical angle. Now notice at this critical angle, the exit ray is rolling along the surface. So if I go beyond the critical angle, I get total internal reflection. It's better than a mirror. It's better than a mirror. That's why optical instruments are often heavy, because they have prisms inside rather than mirrors. And if I do good old Snell's law, so this is N1 and this is N2, and this is theta 1 and that's theta 2. For this example here, this is N1 and that's N2. Got those numbers backwards. And this is theta 1 equals 90, and this is theta 2. So we say, well, n1 sine theta 1 equals n2 sine theta 2. It's just Snell's law. But in this case, it's n1 sine 90 is equal to n2 sine, and we don't call this theta 2, we'll call it the critical angle, theta c. The critical angle is the angle that gives you 90 degrees for the other medium. So if let's work it out for air and water. So let's say that this is air and this is water, because I know those numbers. So 1 sine 90 is equal to 1.33 sine theta c. So sine theta c is equal to sine 90 over 1.33, which equals 1 over 1.33. Theta c is equal to sine to the minus 1 of 1 over 1.33, which equals, so this is going to be second sine 1 divided by 1.33, and I'm getting 49 degrees. So this is telling me this is 49 degrees. Now let's go back and let's have a quick look at this. So I have refractive index of the environment is air, and the refractive index is going to be water. And then I come along and I'm going to try and find that angle. This might, whoa, it's right there, isn't it? It's so close. There. I'm going to take it as that. Get my protractor, come along here. Now remember, great, beautiful. Then this does not work. I'll tell you what I can do. I can bring that down to there, and then I can find that again. Yeah. There. And if you look, that's going to be the angle of incidence is going to be 10, 20, 30, 40. I'm getting 52 degrees on this. And so let's have a look. I said 49. The experiment's giving me 52. EXP equals 52 degrees. Not bad. That's prediction. Got a minute and a half. Just write this up. It's not a lab in the traditional sense. It's a lab in the sense of let's practice some of this stuff. I hope it worked out. I hope you could follow it. And I'll see you next time.